So good morning, everyone. Thanks for being here. First of all, let me thank the organizers. It's really a pleasure to be here. I think it's really interesting to gather all these communities together, and hopefully we can do something useful for our world. So, okay, in this talk, it's not directly about energy consumption, so it's really fundamental research. But as you will see, I think it goes into the direction in better understanding what we can do with dissipation and maybe do something useful with it. So the title is Quantum State Tomography of 2 qubits from Currents and Noise. So quantum state tomography, probably you all know about it, no? It's about reconstructing the density operator of a quantum system. So here I put some images that I took from this paper. It's an experiment which was done in the group of Andreas Wallraff at ETH in Zurich in Switzerland. And it was, okay, with superconducting qubits, it was one of the first 2-qubit tomography. So here, and I will explain it more later in the talk, but this is the reconstruction of the density matrix, and this is a setup with the 2 qubits, so qubit 1, qubit 2. And so to do this, as I will explain, they need to perform projective measurements onto their 2-qubit system. Now, I will explain you how maybe we can do it in another way in the context of open quantum systems. So an open quantum system is a quantum system, for instance, the 2 qubits here, also in red and blue, which are interacting with some environment, and here I just depicted some thermal baths. And if there is some out of equilibrium situation induced by a temperature gradient between the two baths or a voltage bias, then there will be currents flowing through the system. And what we did is to propose a way to extract information about the density operator from the currents only. Okay, so this research was done in Geneva in the Department of Applied Physics that you may know mostly for quantum information, for research done in quantum information theory, quantum communication. So we have a few colleagues working in theory and doing experiments. And so my topics of interest are, in general, quantum dynamics, quantum thermodynamics, quantum transport, and so quantum information. And the results that I will show you were derived by my postdoc, Gian-Michele Blasi, whom you can see better here, and Jeanne Bourgeois, who was a master's student and who is now a PhD student with Vincenzo Sabona at EPFL. So I acknowledge them for their hard work. So okay, let me introduce you the idea. So let me start from the beginning. If I have a 2-qubit system, I can describe it by its density operator, which I can write as a matrix, choosing some basis for the Hilbert space of the 2 qubits. Here, I denote the 2 states by G and E. And this is my density operator, where here I have the populations, and here I have the off-diagonal elements, which are the coherences. And now I already see a mistake, so it should be E, 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 and of course, these are, well, you know how to deal with the indices. But and this density operator should describe the state, for instance, of these 2 qubits in the experimental setup that I already showed to you. So now what they did in the experiment is to initialize the 2 qubits in a given state. So they can choose, in the paper they did it for the 2 qubits in a separable state and for 2 qubits in an entangled state. So, okay, here I think in the community it's clear that why entanglement is interesting is that it can be used for many, many tasks in quantum communication, quantum sensing, quantum metrology, and for the main directions for quantum technologies. So this is one form of entangled states. I just show you this. And so if you compute the density operator defined by this, you can just represent the real part and the imaginary part of the 16 elements of the density operator with tomograms. So it's like histograms for a density operator. And so this is what it should look like in theory. And this is what they got in the experiment. So you see that there is, okay, we recognize that there is some highest populations for these elements, which corresponds to these elements. For the imaginary part, it also, well, the two main tomograms are also the same, but still it's quite different. No, it's not a perfect map. But what is important is that if you account on the theory part for finite photon and qubit lifetimes, then in fact there was an excellent agreement between theory and the experiment. So how do they obtain this kind of tomograms? No? To access the different elements of the density operators, you have to do projective measurements onto your 2 qubits. So they do these Pauli measurements, no? By applying the unitary, and these operators are all the combinations, for instance, of the Pauli matrices. So, for instance, they measure the single Pauli matrices, no, sigma x, sigma y, sigma z, and then they do all type of combinations, and this allows you to access all these elements. Of course, they do this measurement, and then the idea is that, okay, they redo the experiment. No? So they reinitialize their qubits, they remeasure, and then they do some statistics over 6.6 times 10 to the 5 repetitions of the experiment, and then they can calculate some fidelity. As it was said in previous talks, no, you can perfectly reconstruct your density operator if you will have an infinite number of measurements. No? So this also concerns us because then you need an infinite amount of resources. So what you use are these, for instance, maximum likelihood method to ensure that your density operator is positive, and then you, with a certain confidence, you know what is the state of your 2 qubits. So this is like how quantum state tomography is typically performed. So if now I take a step back, and I want to provide a more general view. So this will be a chip. This is an IBM chip with the seven qubits that are here. And so you would like to interact with these qubits, for instance, to do quantum state tomography. And so typically this is done by external drives, typically in the microwave regimes, because then you can implement your unitaries, and so you can do logical 2-qubit gates, you can read out, do the initialization, do quantum state tomography, for instance. So this, it works very well, no? Now, in the last 2 decades, we have, or experimentalists, have really gained some expertise in letting a quantum system interacting with different kinds of environments, and for instance, with engineered baths. So engineered baths are, for instance, a finite number of qubits, or for instance, baths with which you engineer the dissipation. So this was used, for instance, to stabilize your system in a decoherence-free subspace. And why it works, again, in fact, it's because you control the number of degrees with which your quantum system is interacting. So that's why it works well. But typically, one wants to avoid dissipation with thermal baths in the sense where it's uncontrolled dissipation, so you really have heat flowing out of the system. And so this is why now for quantum technologies, people are asking, okay, what can we do even if we have a small amount of noise or of dissipation that we do not control? And this motivates some of the question in the NISQ direction, or this also puts some fundamental limits on for metrology. But we know that dissipation, even if it's uncontrolled, can still be a resource. And in particular, if you have two thermal baths. If you just have one bath, okay, it's a bit harder to exploit it as a resource, but still you can, especially if it's a zero temperature bath, and you can cool your system to the ground state, and then we know that we can do interesting things. But in general, it's easier to take advantage of two baths which are biased in temperature or in voltage, as we know from the 19th centuries. So the question now, as I think you already understood, that I will ask and explain is how to perform, or we perform quantum state tomography using just these out of equilibrium currents. So the idea is the following. So this is a scheme that you already saw on the first slide. So these are, again, my two qubits. I will explain, but they can interact in many different ways. And what's important is that they interact with some environments which are biased. And due to this bias, you have heat or charge current flowing, so typically from hot to cold, or from the highest voltage to the lowest voltage. And what I am interested in is the density operator of my two qubits. And the density operator here, okay, sorry for the change, but it was more convenient like this. Here we wrote it in this canonical basis where the states are 0 and 1. Okay, so you have the four populations, and you have all currencies here. I just show 4, but there are 12 currencies. Okay, so why is this system of interest in particular? Is because in previous works we have shown that, in fact, thanks to this current flowing through the system, we can have entanglement between the two qubits. So, and this can be seen with these two plots. Here you see I show you the heat current as a function of the temperature bias between the two reservoirs. And okay, as it is very intuitive, as soon as you have some difference in temperature, you have a heat current flowing, and here I show it for energy degenerate qubits. If I now show you the concurrence as a function of delta T, so the concurrence, before I explain this plot, it's a measure for entanglement, and so it's 0 for separable state, and 1 for maximally entangled state. So you have entanglement, so quantum correlations, as soon as concurrence departs from 0. Okay? So you see that if I plot the concurrence as a function of delta T, at some point, I also get a finite concurrence. And this can be, at the beginning, rather counterintuitive, because it's not that I implement a unitary logical gate between the two qubits. They do interact via a certain interaction Hamiltonian, so this cannot be any interaction Hamiltonian. And then I just let currents flowing, and in the steady state, I still have entanglement. So it means that my currencies did not vanish completely. So that's why it's an interesting system for studying the generation of entanglement from dissipation. And so what we showed, and I will explain you briefly how we did, is that from the currents, so flowing from the left and right reservoirs, and from the cross-correlation noise between the two currents, okay, we can access the populations. That's enough to reconstruct the populations. And now we must also access the off-diagonal terms. And for this, we propose to use the time derivatives of the currents. And I will show you why it works. But this is our main result. Okay, so now how does it work? Let me give you some details. Of course, it's an open quantum system, no? So the system evolves in time due to interactions with the environment. So in fact, you have to describe the quantum dynamics of this open quantum system. So you have to choose some evolution equation to know what is the steady state or what is the state at time t of this system. So we choose a master equation approach. And this approach is valid when the system is weakly coupled to the bus, which is relevant for many experiments. But you see, it's not the only condition because the two qubits do also interact between them. So in fact, for this approach to be valid, for obtaining a valid form for the evolution equation, here we must also assume that the interaction strengths are of the order or smaller than the coupling to the bus. Okay, so that's the technical details, but it's just to be precise. And how interaction works with the bus is described here. No, you just have a quantum system, and an excitation can flow into the system or can flow out, or gamma plus, gamma minus. And of course, this happens with a certain probability, and this probability is set by some Baire rates and the statistics of the bus. Okay, so this is all what you need to know. So then we have a two-qubit Hamiltonian. So we choose a general one, with some Baire energies for the left and right qubit. The qubit can, in principle, also have some Coulomb type on-site interaction, not on-site, but between them, some Coulomb interactions between them. And there can be some resonant interactions, so flip-flop type, or off-resonance. So this will be like, well, if you inject some energy, you can have some non-conserving energy interactions. And then you can write these master equations. So what I just need to explain to you is that this is an evolution equation for your density operator. And it accounts for some unitary evolution, as if the quantum system will be closed, and some dissipative part. And this term here describes dissipation with the bus, and you recognize the rates gamma plus, gamma minus that I just explained. And here we also account for the possibility for the qubit to have some finite Coherence time affected by pure dephasing channels. Okay, so these are these small errors. And this is just to define these quantities. So now what we want to do is to calculate the current and noise and show how this gives access to the density operator. So this requires some work, okay? And in fact, these results were only possible thanks to a previous work that we have done with my postdoc, Gian Michele Blasi, and Shishir Kandelwal, who was my previous PhD student, where we could really formalize how to compute currents and noise at all times within this master equation approach. Okay, so you can define a current superoperator, but why I show you this is then the right and left currents are simply given by the average of this superoperator with respect to the density operator of the two qubits. And for the noise, in general, okay, if you take a correlation functions between two quantities, so it depends on two times, T1, T2. Here, and this is also the case for this quantity, but here we choose to look at T1 equal T2 equal T, okay? So that's my correlation functions between the two currents taken at the same time, okay? This is why it only depends on one time. And then, again, from this paper, we can write this formally, and it takes this form, which is in fact rather intuitive, because it's as if you would simply take the correlator between the two current superoperators with respect to the density operator. So then you write down, so you have this definition, and you write down what they look like when you inject the evolution equation for your two qubits. And you get this expression for the current and for the noise. And you see that this depends on the population of the left qubit. The right current depends on the population of the right qubit. And this is rather intuitive, no? That the current to the left path depends on the population of the left qubit, and the same for the right side. And the noise depends also on these populations, but it also depends on this doubly occupied population R11. And just that you understand the notation, no? In terms of the density operator, the population of the left qubit is R10 plus R11, and so on. So you see that I get, now this is linear algebra, no? I get 3 equations and I have some 3 elements that I want to access. So R11, R10, and R01. So I can solve this equation to reconstruct my different elements. And the last one, I can access it by using the trace property of the density operator, which is always 1. But so you see, it shows that, in fact, when you measure a current and the noise, that's enough to reconstruct the populations of your system. So, of course, you need to know what are these rates. No? And here I won't enter into many details, but experimentally this can be done. This was again an experiment done by Wallraff and Klaus Enslin in Zurich, where by spectroscopy, you have 2 dots, you have some gate voltages, and in fact, from having the Coulomb diamond schemes, you can reconstruct the rates, and you can even reconstruct some feature of your system Hamiltonian. So this was for the populations, and now for the currencies. So for the currencies, in fact, as you see, for the current and noise, alpha, beta do not appear. So here that's important. It's not that that the dynamics does not depend on the currencies, no? But when you take the current and the noise at a certain time, it only gives access to the populations. So you have to look at other quantities, and what we propose is to look at the time derivative of the current. So you take the current, if you derive it with respect to time, you see to insert what is the derivative of the population, and this again, you have it from your evolution equation. So you get these kind of equations, and so you see that, for instance, you can access the imaginary part of alpha if there is a certain type of interactions between the qubits, and the same for imaginary part of beta. So that's the idea that so you need, for instance, the first time derivative to reconstruct the imaginary part, but these currencies can be complex, so you have to reconstruct also the real part, and this is done by looking at the second time derivatives of the currencies. So maybe it looks like a lot, but it's like tomography. No, there is no magic. To reconstruct the 16 elements, you need, 16 minus 1 measurements. So it's not that by using this technique, we can suddenly, by magic, having less measurements. We still have to access many things. But what we claim is that what we need to access are only the currents that were given for free, anyway, because it's a dissipative quantum systems. So this is like in an experiment. I will imagine that you measure your current as a function of time, and then from it you can calculate the cross correlations by looking at the same time. You can look at the derivative, second derivative, and of course the time resolution of the current traces will determine the accuracy of your reconstruction, but as in any experiments. And to conclude, what is, I think, quite exciting is that you see now we can access all elements from transport quantities. But so it means that if you have a quantum system and you want to certify the presence of entanglement, you have to compute the concurrence that I already mentioned. And for instance, for this kind of density matrices, it takes this simple form. where it only depends, you see, on the absolute value of the currencies and on the populations. And so now, in fact, we can provide an expression of the concurrence based on transport. So thanks to this work, we could propose like a transport-based witness for entanglement. And in the steady state, it takes a rather simple form, you see, where you only have the steady state current, the noise, and some rates. And so it means that if I go to a lab, and I want, the people doing the experiment, they can measure this current and say whether or not their qubit is entangled. Okay, and so with that, I conclude. So I think this work shows that, in fact, we can access complete state, we can perform complete state tomography with transport quantities. So the idea behind now is to extract all possible information from the environment. And the more fundamental question is, in general, what can we learn from the environment about a quantum system? And here in this case, so we show that complete state tomography is possible. Of course, in the steady state, it's simpler because all time derivative currents vanish. And so we exploit out of equilibrium situation, and we need, some information about the system, but this is also reachable in current experiments. And so the results will be on the archive next week, I guess. And as a perspective, I think, you see, it also in the context of this conference, it's a question is how to estimate the cost of a process for processing quantum information. And so here it's like an autonomous way to perform quantum state tomography. So it's maybe another way to estimate the energy cost of such a problem. And then, of course, we would like to generalize it to multi-qubit systems and to really estimate a bit the errors in terms of the accuracy of the current traces. And with that, I thank you for your attention.
Thank you, Géraldine. So the floor is open for questions.
Hi, thank you for the talk. I was wondering, the model you take for the master equation, is it with local or global coupling to the bath?
So it's local. Yeah, local in the sense that each bath interact directly with like the degrees of freedom of one qubit. If the qubits are strongly interacting, then the relevant basis is the energy eigenbasis. So then the dissipators are different. And the expressions, we have looked at this, are like much more complicated. So analytically, it's very difficult. But you see, it should also be possible. But then I think you have to go to numerical results. But what this work shows in this situation is that, in fact, all the information is in the current and so on. So then you maybe have to play and combine different quantities, but I'm sure it works.
Okay, thanks.
Thanks for the talk, Géraldine. I have two short questions. First, I didn't really get, you said that the coherences you get from the time derivative of the current, but what exactly do you compute? Is it like the correlation function of the derivative? Or?
No, it's just the time derivative of the current. So it's really, you take this current trace, and if you want the derivative of the current at a certain time t, then you take a small delta t around to compute the derivative, and this is enough. But that's why it depends, you see, on your time resolution of your current measurements.
But then it's the average current or the stochastic?
It's the average current.
Okay.
Here, everything was done in the framework of average master equations.
Okay. And more in the direction of the generalization that you said. I mean, would you think that for like a more general system, you would need like kind of higher cumulants or something like that, or what's your kind of
Well,
intuition?
yes, because you see, multi-qubit, it means that the size of your density operator increases. So as if you would perform tomography as we knew until now, you need more measurements, no? So you will need more things. Now, with this system, you see, it was enough to consider, for instance, cross correlations at the same time t. Of course, then I have lots of freedom. I can also look at different times. And then this will involve more elements from the dynamics. And then this gives me some freedom to add quantities for getting more equations and for solving the multi-qubit thing.
Thanks, Géraldine. It was really nice. So I have kind of a follow-up question. So if it's the derivative of the current at steady state, I guess
Yes.
it's always zero. So do I really have to rely on the transient to get the coherences? And if so, what is my time resolution that I would need?
No, okay. So the highest time resolution you get, the better it is, as always. And then, indeed, in the steady state, you see that you get these derivatives which are zero. And so, in fact, the expression of the imaginary part of alpha is only reconstructed from the steady state current. So it's super simple. But for instance, if you have some off-resonant interactions, you see so that the derivative vanishes, but IL is equal, in the steady state, you will think that IL is equal to minus IR, but that's only if energy and current are conserved. But if you have this off-resonant interaction, in fact, you input some energies of particles. That's why you can still access this. So it just gets simpler, and there is no restriction. But the real part, for instance, you won't be able to access them. Yeah. So,
and I have a super quick one. If I want to access the other parts of the density matrix, do I go to higher derivatives?
So thanks for the question, because it's something I wrote, but I did not say. This technique allows you to reconstruct the elements which are involved in the dynamics. So that's why here you see we can only reconstruct alpha, beta, because these were the elements involved in the G-resonant and G-off-resonant interaction Hamiltonian. But if you'd consider a very complicated Hamiltonian, which is coupling like all elements, then you will have access to all elements. So it's just that it's really the dynamics that tells you which elements you can reconstruct. Yes.
Cool. Thanks a lot for the talk, Géraldine.
Thank you.
I have a question about the entanglement part, and mainly in the sense of how is this, say, steady state entanglement accessible? Because I'm somehow thinking about this as you're measuring the current and thereby maybe verifying that there's some entanglement in this 2-qubit state, but every time a charge, say, tunnels into the environment, the entanglement is, I guess, destroyed because you only have a charge on 1 qubit, so there's no coherence anymore.
So be careful, because I think what is helpful to answer your question is to really realize, for instance, that the expression that I showed is the steady state expression. So the steady state regime, Florian, is really, can be sometimes, I think, a bit difficult to understand, but you have a constant flow of particles. So you have really this steady state current flowing through the system. So of course, this steady state current involves some particle tunneling in and out, but your system has reached a steady state. So the density operator does not evolve in time. Also, you have particles jumping in and jumping out for getting a current, you see. But so that's why you can still have entanglement in the steady state, and it's not because you have one particle tunneling out that you lose, that there is nothing in the system to be entangled. Thanks. You're welcome.
Hi, Géraldine. Thank you. Very nice talk and interesting different way to measuring elements of the density matrix. My question was the second question of him, but I have a follow-up. So, from your answer to his question, if I initialize my 2-qubit in an entangled state, that also includes elements that are not in the diagonal or in the anti-diagonal,
Yes.
then in the Hamiltonian is the one you have shown,
yes.
then you cannot measure these other elements from this method. Is this correct?
Yes. If yes, that's correct with what I showed. If you would still like to access this element, you would need to measure, for instance, the cross-correlation noise at different times. And then you will see that these elements, they appear at some point. Of course, in the steady state, they vanish because they are not sustained by the internal dynamics of the system. But at some precise time before the steady state, they will appear somewhere.
So you need to access the transient in this case?
Yes, yes, yeah. But then you have to look also at different quantities, not only the noise at the same time. Yes.
Thank you very much.
You're welcome.
Okay, we're taking a last question, and maybe, Leah, you can plug your computer in the meantime.
Thank you, Géraldine. I just have a quick question about the correlation between currents you're using.
Yes.
There is some kind of lack of symmetry. You use always SLR.
Yes.
Does it have to do with the fact that one bath is hotter than the other? Or could you use just SRL the same way or get different
yeah, so thanks for the question, Alain. In fact, so you could use SRL, you could use SLL, you could use SRR, okay? It's just that, let me say that in the steady state, if you have conservation of particles and energy, all these quantities are related. In the steady state, SLL is equal to SRR is equal to minus the cross-correlation functions. Okay, so in the steady state under particle conservation, they are related. In general, they are not, and at finite times, they are not. So the expressions will look like a bit different, but the type of information they contain is the same. So we just choose that one because we thought it was nice to have these cross correlations between the two current traces. But in principle, you can have other quantities.
Here again.
Thank you.